start, I'm going to talk about PNL tools for Randomise today, which is FSL's statistics tool. Well, although my focus is letting you know that there are tools that we can use very simply in PNL to help you check the result and run them randomized, I have to talk a little bit about the very basics of general linear models and FSL Randomise. So general linear modeling is a kind of linear regression that allows you incorporating various statistical tests like t-test and f-test very simply and easily. So just to quickly recap what linear regression is. So when given a bunch of information variables like x here and their corresponding y, we come up with a straight line that best fits the data. Then we statistically test whether this line is steep enough. In other words, is the gradient different from 0? So we estimate the line and then test it whether it's different from the 0. So once we have the significantly different gradient in that line, we can use that line to predict the values of y using given value of x. So say we have new data that comes in with x50, we can predict that y has probably value around 12, okay? Such as predicting weight based on height, or predicting daily calorie income based on weight, something like this. So estimate the line, and statistically test whether it is different from 0. Okay, there can be more than one. Let me put the face a little bit smaller. Okay. There can be more than one independent variables like this. So a bunch of x's and corresponding x2s and y information can be used to form the plane that best fits the data. Then, statistically test whether these beta values are significantly different from 0. And again, if so, we have the model that can be used in prediction based on x and x2. Okay. One example can be like exam grades can be predicted based on IQ and study time. So this time again, get the gradient and test the gradient whether they are different from 0. If they are different from 0, we have the model to predict grades based on IQ and study time. Another boring example, housing price, size, number of bedrooms, and average income in the neighborhood can be used to predict. Again, we get the gradient and hypothesis testing. Are they different from the 0? Okay, so general linear model, GLM, is very similar to linear regression in that it is linear and it can have more than one independent variables, but it takes independent and response variables in the array format. So we can take more complex variables like the ones that we use, like MRI images, FA maps, 4D maps, and stuff like this. And also, since the input and the variables are in matrix format, we can combine this with something called contrast factor in a way which describes how to mix the input matrix for different purposes. So you can test more complex statistical models like ANOVA, ANCOVA, and t-test, or f-test on your data. As a simple example, you can estimate a beta map for age that can predict FA map patterns. In other words, find the cluster in the FA map that shows correlation with age, and then test whether this beta map is significant. You can do something similar to it, age and sex as the independent variables, and get the beta maps for each, and then test whether the beta maps are significant. Okay. But for us, for people in PNL, it is more the group comparisons that we are mostly interested, finding whether there is any voxels that show significantly higher or lower values in one group compared to the other. So this is how our GLM would look. To go a little further in this, so in order to run something like this, you need independent and response variables in arrays. So this map is each individual's FA skeletons concatenated into one file. So it's a 4D skeleton. since each subject has 3D skeletons and is merging into 4D. Okay, and we need a matrix input like this, representing which group the subject was belonging to. So the first 3D image here in 4D skeleton is coming from the first law of the subject, which had value of 1, 0. So here, this column represents group 1, and this group represents group 2. The first subject was in group 1, since it was 1, 0. And second subject, the second 3D skeleton subject was 1, 0 as well. So it was group 1, group 1, group 1, and vice versa. And the last subject was 0, 1, which shows you the last skeleton was from a subject who was in group 2. So inputs are matrix, and response variables are matrix now. Okay, and we use this format along with a contrast vector that looks like this to run the statistical test that we want to run. So if you are interested in a region that is significantly higher in group 1 compared to group 2, you give a contrast that is 1 and -2. If you want a region, the region with a significantly increased FA map in group 2 compared to group 1, you give 1 and -1 here. So -1 and then 1. Okay. So in summary, it looks like this. So merged FA maps that we get from TBSS, and then you get matrix here, which is called design matrix. And then we mix these design matrix and the response variable that we have with each contrast to run the statistical test that we are interested in. Here we are running 2 tests. First test is finding the region where the FA is significantly increased in group 1, and for contrast 2, where is it significantly increased in group 2 compared to the other group. Okay, so we can also include another independent variable like age or sex. So your matrix, design matrix will look like this. So first subject is 1, 0, representing group 1, and you add an extra column for age, and you can add extra column for sex. Okay, so this column represents age now. And then in the contrast, by adding 0 in the spot for the age column, we can take the effect of age out from the group comparisons. So this time we are saying find the voxels with greater FA in group 1 compared to group 2, taking account of the age. Okay, it's quite simple. And the other way for the other comparisons, we are just adding another column that we want to take the effect out from our comparisons by adding 0. So again, to summarize, 4D matrix skeleton, and then design matrix input, and then we use different contrast to pick the statistical comparison in interest. All right. So FSL Randomise is a tool that runs general linear models for FSL. It works for TBSS. So it estimates the beta parameters and then tests the significance using non-parametric permutation testing, and then does multiple comparison correction using FWE or TFC. TFC stands for threshold-free cluster enhancement. If you're more interested in statistics, go back to FSL site, and there's a paper on this. So then they output the statistical maps in nifty formats. So if it was a t-test like 1, 0 that were given, then they also give out t-maps and corresponding p-maps, and also multiple comparison corrected p-maps. This is what we want in the paper and in your project. So we look at this file and then see whether the contrast resulted in a significance. So this file, p corrected maps, has a naming convention like this. So it has a prefix that you choose, and the multiple comparison correction method that you chose, which was TFC for this time, and then CORP, which represents that is corrected for multiple comparisons, And then number of contrast here. So you give contrast in a vector in each lines. So this will represent the line that this file was testing for the contrast. Then the output file, if you open them up, it will be in the shape of skeleton for TBSS. And each voxel will have a p-value, but it has a p-value in a reversed format. So it's like a 1 minus p-value. Just know that. I think it's for the visual purposes. So if you have any voxel that has a value greater than 0.95, then you have a significant statistics for the contrast for that voxels. Okay. I know it can be a little confusing if you haven't ran FSL Randomise for yourself, but don't worry about it. You will understand that. You will definitely understand it better once you run it for yourself for your own project. And it is really well documented. So if you want more than like a t-test or f-test, you can just go Google FSL GLM, and there's a bunch of contrast that you can use. It also can do, you can also do repeated measures, uncover stuff like this. So don't worry about it. So I have a practical that we can run together. So so this step, you've done it with Tashiv last time. So running TBSS using TBSS, which is piano script for running TBSS, which uses ENT and normally ENIGMA-template. And what comes next is you need to create the design matrix and the contrast for statistical testing that you want to do. And then after making this, you run general linear model using FSL Randomise, and then you check the results. Okay. I have a fake data that has a bunch of patients and bunch of healthy controls, and which already finished running TBSS for FA and FAT and free water. So let's connect to no machine and check, just double check that you have all the values like that. And for those who are actually following what I'm doing, you can copy these into your home directory. I'll do it like this. Okay, I already copied this directory into my directory. It has a bunch of files, but ignore most of them. Do ls star nii.gz. Then it will just show you the nifty files that you have. So these all underscore FA skeletonized and all underscore FW and FAT. These maps are output from the TBSS and TBSS as well. So these are the concatenated 3D skeletonized FA maps, FW maps, and FAT maps for all the subjects that you included in the project. And this, you have a mask, and this is mean FA maps, okay? And you have to ignore this map. Let me remove this. Okay. So the files that I showed you, these files, all the nifty files that start with all, they are a bunch of skeletons merged together for all of the subjects with each modalities. And let's check the information of the file. So let's check one of the file. So I'm checking FSL info on FA skeletonized. Then what you can see is that for the fourth mention is 135, which means it is 40 file with 135 3D volumes. Okay, this also represents the number of subjects that we have. All right, go like this. So now we have FA map. What we need is the design matrix now. Okay, we need design matrix that looks like this and design contrast for the statistical information that we are interested. We are interested in group differences. So where is it greater in group 1 compared to group 2, and where is it greater in group 2 compared to group 1? Okay, taking account of the age. The contrast looks like this. Okay, we have 53 health controls and 82 patients, and the way the skeletonized images were concatenated were all the healthy controls come in first, and then the patient images, just like this, and is ordered in that order. And I also put the demo.csv file, which looks like this. So it is vital to have same subject in the 4D skeleton and the matrix in the same order. That's the vital part in the TBSS randomize. We have to have them in the same order in the 4D matrix and the design matrix. They are, for this case, I double checked, and this is the demographic table in CSV. You may have in Excel files. Okay, this is how it looks like. So let's start creating the design matrix. There's a function called design_t-test2 is provided by FSL. You can do design_t-test2, and then output name. I want to create something called design, and then you give number of each groups. So 43 in health controls, which comes first, and then 82 patients, which comes later. If I do this, it creates met file and conf file with design as the prefix as I've given them. Let's see how they look like. Let's see how the design con first look. It looks like this. So it's just a simple template that you can use for the group comparisons when you have two groups. It's testing, is group 1 bigger than group 2? Is group 2 bigger than group 1? Okay. And if you look at the design met, it looks like this. There's some headers, how many columns that you have, how many number of points that you have, how many variability that you have in the each columns, and then goes on metrics. The first subject, second subject, third subject, fourth, and so on. So these subjects represent group 1, and 0, 1 represent group 2. Okay. Okay. So now we need to add the age column from the design matrix. So I'm in demo.csv file. There's loads of ways of doing this. You can use Excel, you can use LibreOffice, you can use gedit, or you can use Python. There's a Python example that I included in the PDF. I'm going to send you the PDF if you're interested. But this time we're going to do it with VI. This is easier. And most of you already know VI. So I'm going to open up design met. And I'm going to open up demo CSV. Since they are perfectly ordered, I can just copy the age column into here. What I do is I change the number of waves into 3 because there will be 3 columns. And this PP height is the difference between the maximum value and the minimum value. You can use Excel to get this. And it's 40 for our case. Select all the age and then paste it here. Okay. We've done VI and you know how to do this. Okay, I'm going to save this. And your design mat looks like this now with age, okay, with 3 columns. And now let's change design mat. Design con, design con. So number of waves will be 3. There will be additional column for age, and you just put 0 in it. Number of contrasts is still 2. PP heights, maximum and minimum difference is 0. Save them. Okay. you just created your design matrix and design contrast. So if you haven't done it, if you couldn't follow it, you can just copy them. I already made them. You can just copy them. I'll leave them on the screen so you can follow. Now let's make a randomized script. So I know some of you have just habit of running randomize here. Don't run it like that. It's better to have script every time, and maybe date and maybe your name or what is it specific for, so you can go back when you have results and when you're writing your results up. So what I do is I open another script called run randomize. And close this. Then it opens a new, this is just a text file. So I'm going to write a randomize commands here. The randomize command is, this is just randomize, conventional randomize for FSL. What you do is randomize, and you give input, which is the merged 4D images, FA skeletonized, .gz. This is output prefix, TBSS FA. It's better to include TBSS in front of it just to make it consistent with other manuals that from FSL, that's in my experience. And then for D option, you give design.mat that you just created and edited. And for T, you give design contrast. Okay. And for the M is a mask that's mask for your template. This time I used Enigma. And N is the number of permutations. It's normally 5,000 or 10,000. And minus T2 in capitals, this means you use TFC thresholding for multiple comparison correction. Okay, then I save it like this. So this run underscore randomize is saved, and I run this rather than typing this in the commands. So I can have documentation of what kind of commands that are ran exactly. Okay, I'll just run it for the test. For you, just don't run it because it's going to take up the CPU spaces. I'm going to do enter. So it's printing something, so it's running. Give me a few minutes. So it's loading up the files, and 5,000 permutation as we stated, and it's going through the permutation until the 5,000 times. Okay. But in PNL, we have a tool called randomize parallel PNL. You can just change the randomize into this path, which I'm going to ask Sylvan to put this in our general path. So you can just use randomize underscore parallel underscore PNL. So what it does is that it splits the permutations into 100 or 50 different jobs, and then runs them in parallel using BSUF medium queues. So this was made by FSL, randomized parallel, but this doesn't work in the original randomized parallel doesn't work in PNL. So now in RGS servers, use randomized parallel underscore PNL, so you can use BSUF medium queues. I'll show you example. What I do is I just change this into data, PNL, KHO, PNL, BWH, FSL randomize, and then it's inside library, randomize PNL, parallel. Okay, I'm gonna save it. So now your run randomize command looks like this using randomize parallel PNL. Let me run this. You don't run this if you're following something along me, because it's going to take up all the queues. So I'm going to run bash randomize, and it's giving an error. There must be a typo, and it's a typo. I'm sorry. Let me run it again. Yeah, doing something. So it's printing the lines, saying that it's splitted and submitting jobs to medium queues. And then another job for merging them and is in your queue. If you do B jobs, see, your jobs are in the queue. Sometimes it takes a little while to get the queues, medium queues, due to the hospital system. But once you have like more than one comparisons, more than 2 or 3 comparisons, this is way much faster. Okay. And do you remember that we had on other images other than FA maps? We sometimes have FAT maps, we have free water maps, we have MD map, AD, RD, bunch of maps. And if you have different contrasts, then there's a loads of comparisons, and it is much faster this way. We just copy that. So change FA into FW for free water analysis, and change FW into FAT, and you just run this WFAT. Okay, so this is for FA randomize, this is for free water randomize, and the last is for FAT randomize. All right. And this is just explaining what the inputs are, which I already did. Okay. You saw the output. And since you didn't run this randomized parallel with me, so let's copy the data if you want to do something alongside me. I already ran them and put the data in there. Okay. I go into pre-compute. Sorry, I'll copy them as well. TBSS example and Enigma TBSS and stats. Pre-compute 1. Randomize into, I'm going to do pre-compute new. Give me a second. Okay, copy is completed. If you go into the pre-compute and ls, this is the output of running TBSS randomize. 1, 0, 1, 0, 1 minus 1, 0, and minus 1, 1, 0. Okay, so you have 2 contrasts for each modalities, and you see CORP files that we are interested for FA, 1 and 2. So 1 represents greater in group 1, 2 representing greater in group 2. Okay, now you get this. And we have the same map for FAT here, and we have the same map for the free water. Okay, we also see T maps here. Okay, these are the T maps, actual T stat maps. Okay, you have the outputs plus the next. Okay, so just to remind you again, the P maps have the P values in each voxels, but it's reversed. So it's 1 minus P values. So if P is, you are looking for the area where P is 0.05, you have to look for area for 0.95, 0.03, 0.07, okay, etc. So let's look at the range. Let's focus on the FA file. I'll do something like this. And CORP. Okay, we have 2 corrected output P maps, 1 and 2. So what you should do conventionally is you check the range of the values in each nifty images, because that represent the P values. In this way, we do FSL stats, to step 1, and do minus capital R. This looks for the maximum value inside all the voxels and minimum value inside all the voxels. Okay, so minimum value inside all the voxels is 0. Obviously, there's outside the brain 0. And the maximum value in all of the voxels in this image is 0.9949, which is the reversed p-value. So if you convert it back to p-value, is very significant, 0.005 something. Okay, so you have some significance in the map. So you can say in this time, there's some significant differences coming from the contrast 1, which was finding the region which was greater in group 1 compared to group 2, taking the effect of age out from the comparison. Okay, you can find a cluster like this, but normally what I do is I open up with FSLIs, and TBSS, FA, like this. I already opened them. Since the RGS FSL eyes doesn't work, I have to open them this way. So after running randomize, I check each maps like this, TBSS stats, and then minus R, and open them to see where was the significance. Give me a second. So here, what you do is, so you see the skeleton maps. So this is the P maps, which is this. So each voxel has a value of p-value reversed, okay? So what I do here to only see the region which is significant from the contrast 1, you give minimum threshold of 0.95. And the maximum is 1, okay? These are the significant difference voxels from the comparison 1, which was seeing at the significant greater in group 1 compared to group 2. So since this data was from a patient, a large set of patients with loads of commodities, this is obvious that group 1, which is health controls, has higher FA compared to group 2 in all these reasons. Is very widespread. So you can refer to the data like that. Okay, you open them and you can change color of them, and you can overlay the other background tables for your figure and so on, but I'm not going to go in there. Okay, that's what you do with conventional TBSS. But imagine you have FA, FAT, free water, AD, MD, and then ADT, MDT, RD, RDT, and you have subgroups, and you have subgroups of subgroups, and you have different projects. You have your friend asking you to summarize your randomize. Then you easily have more than 100 jobs to repeat like this. This is time consuming and dull and not fun. And not only that, you make mistakes in doing that. Okay, so I wasted my time in making a tool code which is randomize_summary. So it summarizes FSL randomize outputs for you. It just requires, as a minimum input, it just requires the corrected P file, which is the output of the randomize, and design matrix, and design contrast, and the skeleton file that you use in running the randomize. Okay. All this presentation is for a single line of the script. So how you use this is just like this. You go to the stat directory that you see the all FA and all FA TFC corp and corrected T1 and corrected T2, and then design con and design mat. What you do is just type this. PNL, KTRO, PNL, BWH. FSL randomize and library randomize summary and apply. You just type this. So it's loading, it's picking out all the corp PMAP, all the corrected PMAPs, and doing what it did with the conventional way. Can take a while. But it shouldn't be that long. Give it a few more seconds. Okay, that's the output that you see. So it returns a matrix summary, the summary of matrix that was loaded. So the contrast file detected was design.con, matrix file detected was design.mat. There were 135 subjects, and group columns were column 1 and column 2. So and there's a column 3 for another variable, which had a mean of 35.81, standard deviations, mean value and maximum values. From this, we can tell age average for all the subjects was 36, standard deviation of 11.2, and minimum youngest subject was 18, oldest subject was 63, and stuff like this. Okay, but this is what we are interested. Okay, so results summary for FA map. Corp T1 map had a contrast of 1, -1, 0, which means find the region that is greater in group 1, taking the effect of 0. So you just have a brief summary of what it is in an English, and then it was a t-test, and it also grabs what modality was this, so FA. So whether any point was significant. Yes, it was significant somewhere. Okay, what was the maximum p-value? Reversed p-value is a 0.994951. What was the mean of the significant voxels of the p-values? So this just means all of those significant voxels, the p-values were, average p-values were 0.017. Okay, and percentage of significant voxels, it is number of significant voxels over the number of voxels in the mask. Okay, so the change was very significant in widespread area. For the second comparison, which was find a region where FA is significant greater in group 2 compared to group 1, you don't see any significances. So in this case, we can tell there's no area in patient which had greater FA than controls, which makes sense. Okay, for FAT, it was also increased in healthy controls compared to patients, and it was 6.1% of voxels, and that's it. That's what you can do. Okay, that's the basic use. You can also do something like sig only. If you have a bunch of different options, different contrasts and different maps, and when you want to see only the significant images, then you add -- sig only. Then you're only seeing the significant changes like this. And then if you want to summarize this result into a HTML summary, you do HTML_summary. What you do is it runs the same thing. And then it says HTML summary is saved somewhere. Let's open this in a node machine. This is my node machine. So there's HTML created. Let's open this with Google Chrome. _summary. Then you get a summary that was printed in the Linux kernel in the HTML. So data is here. All files are who, it was created when, and a summary of the matrix here, and summary of the contrast, and a summary of the p-maps here as a HTML file. So you can keep this, or you can send this HTML file to your collaborator to show your results. Also, there's another options. You can create figures in this. You can do there's a figure option, -- figure, but normally for TBSS, what we do, we provide TBSS field image. So you provide TBSS_fill and -- HTML summary. then it will run a TBSS fill, which is an FSL command for you, and it will enlarge the significant voxels for the visualization purposes and overlay on the skeletons. So this is running TBSS fill, and this will this script will create a figure in PNG format, so you can check the data quickly without opening FSL view. So give me a second. TBSS fill takes a minute or two. Yeah, I need to clean up the script. It says print haha and stuff. Okay, so it's creating images here for free water map. Now it's doing TBSS fill for FAT. It's nearly there. Give me a second. Okay, let them run. I'll go to the next slide. So there's an option for figure. And this is an interesting option that I can say. So say you have significant group differences in, say, corpus callosum. In corpus callosum, FA was reduced in corpus callosum in schizophrenia patients. Then what you do is you'd like to see the correlation with the FA values in the corpus callosum where there was a significance with the clinical variables that you see in the patient. In order to do this, you have to extract individual values rather than the p-values. So you have to go back to the skeleton. To do this in FSL conventional way, you have to, I'm assuming that you have to split the all FA merged skeletons into each subject and then extract values from each of them. Without mentioning also, you have to extract the significant ROI that you got from the randomized, right? But this script does it for you. So there's an option called subject values. Let me run that. Oh no, let's check the result first. So we just ran TBSS fill option. If you do ls ERTL, there's a figures and Nifty files created. So this is TBSS filled Nifty file, and this is corresponding PNG file. Since we also used HTML summary option with it, it will also updated the randomized summary HTML. So go back to no machine, and if you just refresh this, you have the same finding here, same map. But if you go down, you will have your screenshot of your significant clusters for each comparisons. Okay, you can click them up, and you can see where was it different in each subject really quickly, and what was the comparison and where the data is. This is not for the paper, but you can quickly understand how the comparison, how the group test did. Okay, this was for FA, FAT, and you can go to the free water. Okay, I think the TBSS, I mean the subject-wise analysis is the last one. Okay, let's just run this and see the results. So let's do subject values. So what it do is find the significant cluster and extract all the values for all subjects in that significant cluster. It takes 1 or 2 minutes because you have to load all FA, FW, all FAT skeletonized data, and then extract all the values. Takes a while, but that's the last thing to see here. And while that's running, I'll just end the talk. There's the extra options that you want to see skeleton summary, but this is something maybe could be too much for you, but if you want to try that. And you can also provide the location of the TBSS all outputs, like TBSS _ for more information. And if I do a project, I normally do give options like this, but you don't have to. You can just give single liner or with HTML summary. I think that would be quite helpful for your project. Oh, okay, I'm still waiting for the subject summary, and this is we just saw how the HTML file looked. We have table, we have figures, and this figures is something that you will see soon, and figures, and yeah, that's the last slide. And while this is still running, this is still under development, and let me know if you're interested in making something like this or adding more functions to it. It's still running, but I have ran all of it already in my directory. So let's go in there. Okay, so after running randomized summary with subject values option, you will have this CSV file, which looks like this. So what each column represents is that first column is index, and second column is FA value, free water values in the significant cluster coming from this file, TBSS.2. Next column is FAT values in the significant cluster coming from this file. Okay, so you have extracted free water, FA, and FAT values from the significant cluster for all of the subject. Okay, and it also updates HTML summary that you have. Let's open this. Open this. Table is the same. Table is the same, and you have your figures here. Then on top of that, you have another extra figure. So this is average values of FA in the significant cluster for all the subjects plotted like this for group 1 and group 2. So again, so this is FA average in the significant cluster for all of the subjects and presented for each group. This is FAT averaged in the significant cluster for all the subjects and represented for each group, which can be helpful just seeing how the pattern goes in the significant cluster. And also you have a table that I mentioned. So it also loads the CSV file, which was created in the Linux. It just loads up, and you can copy this information to the Excel or R or Python to run your correlation. Okay. There are a bunch of other summaries of your skeletons. It also, if you use skeleton summary, it also creates summary of the values, like average FA values for all skeletons. I thought this could be meaningful, but this is all extra. So have a play around, and if you're running or if you find the error, please reach out to me. And if you are interested in developing something like this, reach out to me as well. I'll be happy to work with you. That's the end of my talk, and I'll be welcome to have any questions.